Okay, so the second talk of today is by Larios. It is going to talk about the vector to blow up, Inviscid regularization for the 3D Euler and Navier-Stokes equation. Thanks.
Thanks so much. Thanks everybody for coming, and thanks very much to the organizers. I know put a lot of work into this. For me, it's been just an absolutely fantastic time being here. Having a great time and learning a lot. So it's really fun. So I'm going to talk about some older stuff, but I thought it was maybe more appropriate for just sort of talking about blow up and things. We had a great talk yesterday about blow up, and then also some really interesting stuff last week. So carrying on with the theme, we'll talk about this little kind of blow up problem. But disclaimer: no claims of blow up will be made. I'm not claiming that blow up happens or doesn't happen. I'm just I'm playing neutral here just to be safe. But okay, with that disclaimer out of the way, just to set the notation, everybody knows this in this room, right? So just Navier-Stokes, but in incompressible case, and right, we have the millennium problem. But I just want to notice in the new equals zero case, if you show blow up, the millennium problem, if you show blow up for the Euler equation, as far as I know, you just get a pat on the back, right? So no $1 million, right? You got to show, right? Well, opposing us that direction, or blow up for never. So.
At least you won't send a bill.
Yeah. So far as we know. All right. And just to remind, this is a very incomplete list, and many people in this room are on here, or maybe should be on here. But just to give a rough background, so we want to talk about blow-up criteria in the sense that so you look at some quantity and you say, okay, well, this is a quantity which sort of controls all the other norms, or gives some kind of indication of blow-up, gives us kind of a target, especially like if you think numerically, something to look at. So here's just again, an incomplete list of some analytical work. And maybe, I think arguably the thing that started it all is the Voigt-type criterion on the vorticity, right, in infinity. If this thing is bounded, then we have, then we know the solution to the Euler is regular. Computational search for blow up has often kind of gone off of looking at the Voigt-type criterion, but there have been some other works trying to understand, trying to look at other quantities that have been developed. And I would love to talk about all these in detail, but in the interest of time, I'll move on. So there's been a lot of work sort of trying to construct solutions that blow up, and of course the problem with all of this, and this kind of my previous slide, I don't want to make any claims because it's understood you can't make some kind of analytical claim with some kind of about some infinite dimensional thing with some finite dimensional machine, right? I mean nobody's trying to claim that, but we just try to get intuition and build some kind of understanding about what's going on with the solution. Okay. So maybe I won't mention all that much more here because otherwise I will get sucked in talking about things. But kind of on the other side, what do you do? Okay, maybe there's blow up, maybe there's not, but at the very least, there's development of large gradients, right? So what do you want to do? Say computationally, you want to somehow control the large gradients, whatever that might mean. Of course, you want to do this in such a way that if you're doing a simulation, you want to do this in such a way where you're not destroying the large scales. I don't want to have, I don't want to say filter out tiny little puffs of air in my simulation, and somehow that makes the tornado hit the wrong city, right? I want to have something where I can somehow preserve large scales, or maybe other quantities of interest, right? But what do? You got to do something, or you just say, I can't simulate anything, or I'm going to be happy with completely wrong answers, even on large scales. Of course, a nonlinear term mixes these scales quite a bit. So, these are just a few examples. Of course, there are, I think, at one point I saw a list of something like 600 or so turbulence models and things like this. So, right, I mean, it's obviously quite extensive, but just to kind of roughly lump them into a few categories, sometimes you might do something like do some kind of hyper dissipation. This goes back at least to Lyon's, but maybe someone knows of earlier references there. But right, so if you set epsilon equal to 5/4, then you have some regularity here. Another thing you can do, so here this is a viscosity depending on the gradient. So this is kind of Smagorinsky in 1963. Also Larios did some work on this where I said, okay, well, as my gradient gets larger, I'll sort of stuff more viscosity into this region and see what happens. There have been a lot of variations on this. And I would say, I'm not totally sure, but my understanding is that in the engineering community, this is a major industry of trying to find nice viscosities to do. And it doesn't always just have to depend on the gradient. I had some stuff with Jean-Luc Ramond a few years back where we made it based on the entropy residual. I mean, there's all kinds of different choices here. Another thing you can do is try to somehow affect the nonlinearity, smooth out the nonlinearity. So here, Ray put a little modification on the transport velocity there, and of course lots of other things. But just some kinds of things you can do. But I want to talk to you today about not that. I want to talk to you about this model. So we call this a Voigt regularization, and it looks weird. So here you're doing something. You're not direct. I mean, you're not at least superficially doing anything to the nonlinear term. There's no change in the viscosity here. You put on this weird looking term. So you put on time derivative of Laplacian u, and you have some parameter there, alpha squared. Alpha has units of length, as it must, because you're multiplying a Laplacian. We just put a square there so we don't have to worry about the sign, right? And so it can have units of length rather than length squared. And with a minus sign. And why do you want to do something like this? So there's a big history of how this kind of came about, which I'm going to skip in the interest of time, but I'd be happy to talk to you about it, because it seems kind of out of nowhere. But I want to mention this fact. So why is this going to work? Why do I get a control gradients with this somehow? Right? If I take an inner product with u, just say formally, well, we know by a divergence-free condition, if I integrate by parts here, pressure drops out. Nonlinear term, by numerical, drops out by the symmetry and the divergence-free, basically by integration by parts. And so these terms die. And if I set the viscosity equal to 0, just to get a good picture of what's going on, right, and here I'm going to integrate by parts, right? That's now you see why you want the minus sign. Integrate by parts, and I'm going to get a grad u, but with a time derivative on the outside. And this just automatically is going to control gradients, right? Because what happens if I integrate in time, say, then this is a conserved quantity. So it's never going to get bigger than its initial data, at least formally, just talking formally for now. And therefore, this gradient cannot grow very large at all, right? That's one way to control gradients. Okay, is it a good way? Well, who knows? Let's see. This is, the name Voigt here is kind of funny. In the viscous case, this goes back to, I think it's on the next thing. Yeah. So this was studied by Skokov back in the 70s, and who's, I believe, a student of Larios. And he used it as a model for some polymeric fluids, like viscoelastic type fluids. He called it, so the fluids he was interested in particular were called Kelvin-Voigt fluids, right? And so he called them the Navier-Stokes Voigt equations. And from what I understand, it's not all that useful or it's not all that, say, well accepted a model in that community, but I don't know. But that's where it got the name Voigt. So Voigt died 100 years before this model came out, right? But that's where the word Voigt comes from. Okay, so yeah.
Done something similar. What do you think so?
I don't think so. I mean, he was studying Kelvin-Voigt fluid. So there's this type of polymeric fluid called the Kelvin-Voigt fluid, and this was a Skokov's model for a Kelvin-Voigt fluid. Which sort of he used that term. Yeah, so it's just got stuck to it. Yeah, best man knowledge. Okay, just if you want to get excited about it right away. Here's a quick way. It's got the same steady states as Euler, right? And there's right. It's got we're only modifying time derivative, so steady states are the same. Okay. Can we reach them? I don't know. Are they right? But at the very least, we have some kind of stability. Regularization, and I kind of mentioned this before. We call it an Inviscid regularization in the title of the talk because you're not really doing anything. It's not like those other things. You're not modifying viscosity. Okay, so what happened? So this was discovered, I believe, independently by Tao and Austin and Tiki, coming from this from an avenue of something called a simplified Bardino model. They looked at the simplified Bardino model, and then they noticed that this model is globally well posed even in the Inviscid case. So here I'm saying with positive viscosity. But one thing that's nice about this is you're not adding any boundary conditions, right? If I'm say using some kind of hyperviscosity or regularizing in some way, often I'm going to have to mess with the boundary conditions. And here, this thing is globally well posed, which is good old fashioned Dirichlet boundary condition, no slip boundary condition. When you have positive viscosity. But when you have zero viscosity, you notice that you get, you also get global regularity for this thing, at least in a periodic domain. So at the time, it wasn't known, at least I don't believe it was known, what are sort of good boundary conditions for this in the case where nu is equal to 0. But in the last few years, a paper by Berselli and I think Spirito came out, say some nice boundary conditions that can be used for this thing. Okay, but this equation is a little bit weird. The parabolic character of the equations is destroyed, and I want to just kind of show you that really quickly. So I hope people online can still see this. Okay, so if I have something like this, let's just look at the heat equation. I see I put this up too high, and now if I put that Voigt term on it, it's the same as if I factor out a time derivative formula. I get something like this, right? Now let me take the Fourier transform. So I'll get 1 plus alpha k squared, where k is the Fourier wave mode, right? Time derivative of k Fourier mode equals minus nu k squared u dot k, right? And now if I divide, right? So we get something like this. Minus nu k squared over 1 plus alpha squared k squared u dot k. Yeah. So my solutions are going to look something like this. Time and then time initial data. So we get some solutions looking like this. I can't read that writing. Okay, and so you see as k goes to infinity, this sort of the exponential decay in Fourier coefficients. I'm not talking about exponential decay in time, but in Fourier mode, decays. I'm sorry, it doesn't decay, it saturates. Right, you get to a certain level as k goes to infinity. Right, I can just divide minus nu over a minus 2 plus alpha squared t. Whoa. Okay. Right, so as k goes to infinity, I'm going to get some kind of like nu over alpha squared, which if you think about it, is like an inverse time scale. So you have another time scale of alpha squared over nu setting, which is where Skokov was interested, right? He wanted to, and these type of polymeric fluids have, let's say, a secondary time scale, right? Okay, so what does that mean? So you don't expect regularization, right? Basically, you had a Laplacian on the left, so it kills the Laplacian on the right. Well, that's kind of bad. Okay, but what can you say? That's right. If we're interested in the Navier-Stokes case, but Kalantarov and Titi showed 2007 that you actually this thing does have a global attractor even in 3D, and you get and it's comprised entirely of analytic functions. So sort of you recover the smoothness in the limit in some sense. Solution okay, so we just saw that, and yeah, there's kind of a nice result a few years ago by again Berselli and Spirito. As alpha goes to 0 for the Navier-Stokes equation, so hold the viscosity fixed, you get suitable weak solutions for Navier-Stokes. So this is kind of nice. Okay, so let's take a look at this thing a little bit. Here's just a picture of energy balance. So these are some simulation of mine at 1024 cubed resolution. You see you get sort of a increase in the L2, right? This quantity on the left has to be constant because the quantity on the right is constant. So you see the constant lines up there if you add these together. But if you just look at the L2 norm squared, you get sort of a rise, and then the say the entropy times alpha squared, you get this sort of decay. So it's sort of, you have this energy shifting to higher and higher scales, and you just have this kind of thing. I'll show you some simulations in a little bit. Here's some picture of the, so one question is it doing anything interesting? So here's some pictures with zero viscosity. This is just starting from Taylor-Green initial data, so just sines and cosines that are divergence free. Simulate out, and this is these are vortex tubes, vortex structures. You let time go a little bit further, and you get something like this, which isn't, it's not just noise. There's right. This is a well-resolved spectrum at this point. Okay. A couple of things about it. So I mentioned global closeness was proved back in 2006. We proved with Andres, we showed we have higher order regularity. So if you start with initial data in HS, it remains in HS. Start in H17, you're remaining in H17, but it never gets any smoother than that because you sort of destroy this smoothing property. Okay, so all right. We also want to prove, so this is my PhD work, so this is a long time ago, but you want to prove some kind of convergence, right? And so you subtract the equations, you do some energy estimates. It's kind of annoying because there's a time derivative that shows up. But we're able to show if you're on the time interval, so for most of the talk now, I'll not have viscosity until at the end. If you're before blow up time for Euler, right? So everything's fine. Then you can prove this kind of a bound. So you get some convergence, but only in the L2 norm. Notice you get this alpha squared hanging out here, which isn't so nice. But in particular, right, just throwing away this term, you get convergence uniformly in time and in the L2 norm. Convergence order alpha. Okay. But now, if we go back to this guy, where it was, this energy balance, right, just from integrating that equation, right? Where'd it go? Yeah, so we have this energy balance, which Talgunas and TT proved holds rigorously. So what happens, right? So you're going to set alpha to 0. Okay, on the right is time independent. You don't care about anything. So that extra gradient term is just going to die and it's multiplied by alpha. On the left, well, you have convergence in the L2 norm, right? So sort of this guy will converge. So if you have convergence in norm, that means the norms themselves converge, right? So the U alpha L2 norm will converge to norm of Euler. Well, we know that Euler's L2 norm is conserved at least before the blow-up time. So that means if this term in the middle doesn't go to 0, you get blow-up. Right, so take a limit as alpha goes to 0, and you get this extra quantity. So we have this little blow-up criterion, right? If you send the limit as alpha goes to 0, and you get something positive, you have just detected a blow-up in Euler. And that's what I mean by a backdoor blow-up. And I'll talk about this a little bit. By the way, if you don't like it being a gradient, well, don't worry. Remember that we have entropy for divergence-free functions. You have this identity that you can just write. Grad U is equal to curl. Grad U L2 is equal to curl U and L2. So you get you can phrase all this in terms of vorticity if you like. And by the way, a blow-up criterion like this actually first place I know it came out was actually for S2G equations, Inviscid S2G. So completely no diffusion whatsoever, and you put on this regularization, you get a similar criterion.
What is the criterion?
So the criterion, so I'll look at it a bit in slides coming up. So it's good that we talk about it a little bit. So you want to look at L2 norm of the gradient, and if that times alpha as alpha goes to 0 does not go to 0, then you've detected a blow up. Sure. Yeah. It's sometimes we call it one way.
Right.
Yeah. So it's not two ways as far as we know.
It's a condition.
Sure.
Law is that L2 gradient of the velocity times alpha as it goes to 0 is greater than 0.
Yeah. 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 If this thing doesn't vanish and alpha goes to 0 limit, then Euler must blow up. on that same
Euler
comment.
Voigt must blow up.
No, that's the point. And that brings me to my next slide.
That stays.
Actually, 2 slides from now. Yeah, let me go here, right? So the idea is that this is a condition. So Euler-Voigt we know is globally well posed, so there's no problem there, right? And in fact, it's globally well posed backwards and forwards, because it's basically acts like an ODE in infinite dimensions, if you think about it. Okay, so what's happening, right? So this gives us a condition on 3-dimensional Euler equations. So this is the idea, right? If you do Voigt-type, you're say you're trying to simulate equation or prove analytical results about an equation, say 3D Navier-Stokes. Oh, sorry, what did I say? 3D Navier-Stokes. Excuse me. Let me back up a little bit. Yeah, if you're thinking about Voigt-type, you're simulating Euler equation, which you don't know if it's globally well posed, in order to understand something about whether it's globally well posed. Okay, well, this is kind of, I don't know, it seems a little fun. Yeah.
Coming from Euler-Voigt.
Yeah.
Alpha equals to 0. And if that is obeyed, then it's possible there's a singularity in Euler.
Not just possible, there is a singularity.
Oh, there is.
Yes.
In other words, you take that initial condition, you follow it, and you will get a singularity.
Yeah. So you start with an initial condition, you simulate forward in time, you send alpha to 0.
So you're telling me that Euler, that L infinity of Euler, go to infinity.
Yeah. Which follows indirectly, because basically you're just saying Euler loses energy conservation.
It loses energy conservation.
Right, and if Euler loses energy, the only way Euler can lose energy conservation is to become no longer regular. Because if Euler is regular, then you have energy conservation.
There's something wrong with this.
Okay. All right.
The assumption which is imposed is more or less, not precisely, that there exists T less than T star such that the limit suit is positive. So you don't need actually the supreme order, it just exists T.
Yeah.
And so if there exists T which is less than T star.
Yeah, I mean, this is how we stated it in the paper, but yeah, right. If you're right, if there exists T star, so you say, okay, I think there's blow up at time 29. Okay, so I'll simulate from 0 to time 29, right? And I'll look at the gradients of my simulations, and I'll send alpha to 0, right? So really have to do a lot of simulations. And as I do that, I'll get some kind of rate, I guess maybe some dependence of this on alpha. And if the dependence is such that when I multiply by alpha, I can take a square root if you like, I get something which is not going to 0. Then
But the conclusion is stronger because under your assumption, if that is true, you also can prove that the singularity develops before.
yeah. So there's that means there's a singularity in that interval, from 0 to 29 or whatever that would be. Yeah.
Can I ask a question? How do
Please,
you
yeah.
know singular limit taking off 0?
Oh, we're not taking a limit. So that right. We don't know if the limit exists. So that's why we take a lim sup, and lim sups always exist.
How do you know your regularized system captures anything about order?
Don't. I don't. Well, okay. I mean, if this thing, okay. So we do know a little bit. Okay, that's not quite true. We know this. So right. This whole thing is based off this convergence criterion. By the way, I love questions. This is most questions I've ever gotten about this, which is very exciting for me. So we know we have this convergence criterion as alpha goes to 0, right? Before the blow up time. So if I'm before the blow up time, I drop out this this piece. I send alpha to 0. If I'm before the blow up time, then Euler-Voigt converges to Euler in L2 norm, very weak norm, right? I mean, we're not talking about gradients converging here.
If that is happening, you should use numerics.
Yeah.
If that convergence is happening.
Well, I mean, this is a theorem. I mean, this convergence holds.
Can you hear me, guys, or you cannot hear
If
me?
that happens,
Can you hear me?
but you're doing numerics. How do we know you're doing numerics? convergent to what?
Oh, I mean, this is a good question.
They only got two solutions.
Slow down.
Yeah, I mean, this is assuming that we're before the blow up time, we have convergence. And analytically, we have convergence. Whether or not numerically we can, I mean, that's a subject for debate, right? Are the numerics capturing Euler-Voigt correctly and this kind of thing? But
No, well, that's my question. I mean, that's what I'm concerned about.
okay, yeah, well, I'll show you the simulation and you can judge whether or not you think it's reasonable. But at this point, it's just an analytical criterion. So if you could prove, right? If you could prove, which obviously I don't know how to prove this, that this thing is positive, you proved Euler blows up. If you prove this thing is zero, you prove nothing. Other than maybe you should forget about this criterion or condition, whatever you want to call it. I'm not sure if I answered the
Yeah,
question.
no, yeah, sorry, I missed that.
Great, good. I like this. Okay, cool. Quick side note, which is not really important, but we showed you could also swap these limiting conditions. You get a slightly stronger condition, but which is a little bit more useful for numerics because, right, computationally, if you send, like as mathematicians, we just think, oh, let's send alpha to zero. But that's really hard to do computation, right? And I have to do a whole bunch of simulations for different alphas and kind of paste them together, which I did. Show you. Okay, right. So I like this idea that you're sort of starting with something you know is globally well posed. You're doing some simulations, or you're checking, you're doing some analysis, or whatever. And at the end of the day, you learn something about whether or not it's a slightly different flavor. Right, and you don't really have some kind of this is, I think, obvious, but you don't really have something like this for Navier-Stokes in the sense that we don't know if Navier-Stokes is well posed, so we don't know if we're taking, sort of starting with something which is well posed and sending you to zero, sending viscosity to zero. We don't know if we're sort of well posed in the first place. Okay, I think that's it. Oh, right. Okay, so this is kind of what what Bob was asking about a little bit. Right, so the idea is, now we have kind of some approach. We can say, okay, well, let's look at the gradient in the L2 norm, right, and see how it depends on alpha. I'm not going to use this notation again. I just want to tell you that I'm thinking about this as a function of alpha and also as a function of time. But what do I want to do? Well, this means that if let's just suppose for a minute that the gradient of this U alpha is like some power function of alpha. Well, by multiplying by alpha, right, if the power is less than or equal to -1, then there's a signature, or say, this is some kind of sine of law. Right? This is telling us that if we can prove, P is less than or equal to -1, then the thing blows up, or it blows up, right? Okay, so we tested this. So we tested this with Taylor-Green vortex. Actually, we tested this with some other initial data originally, and it didn't. We weren't getting that well. We weren't getting. So right, the game is now to see if you can get a p less than -1. We tested it with some kind of very smooth initial data. Well, this is very smooth. Some other initial data where we didn't see any kind of blow up at all. But then I was talking with an equivocation. Hey, why don't you use Taylor-Green? So we did. And by the way, Taylor-Green is kind of nice because so this is a Taylor-Green vortex, or one version of the Taylor-Green vortex, right? Just some sines and cosines. And for this one, Brachet and company predicted back in '83 that you get a blow up at time 4.2. And there are several studies they did after this where there's sort of higher resolution and new tools and things, but so this blow up time of 4.2 seems to be what they predict. Okay, so I did some simulations, and this is just a picture of the spectrum, trying to convince you that the spectrum is well resolved, although I wish this picture went a little bit lower. So spectrum dies before the 2/3 line. And you can kind of see that if you're interested in the dynamics of this. So the blue is the initial condition spectrum. So I don't like average spectrums as much because I kind of like to see what's going on at every moment in time. I mean, nothing against average spectrum, but you let time go, and you see this sort of cascade to the higher wave modes. That's exchange I showed you before between energy and the L2 norm and energy and the gradient is happening here, right? It sort of just keeps getting pushed out further right. The black line there is the final spectrum. So it sort of goes up and then falls back down a little. Okay, so we tried something. Yeah. And we did simulations at a bunch of different values of alpha, which you see here. There's 1,024 times alpha, and looked at just how, so what we want to know is, what is this thing as alpha goes to 0? So each of these represents a different time, right? And this is what I was telling you about, this annoying thing about it in simulations. We can't just send alpha to 0. Instead, you simulate out this way for a bunch of different times, and then you pick another alpha and simulate this way for a bunch of times, and then you stitch everything together, right? At the end of the day, so then these curves are sort of drawn in after the fact. But yeah, so this is the this L2 norm of the gradient, and max in time. Up to a certain time, and then so here that thing for different alphas is kind of shallow, and then as things increase, it gets steeper, and what you're looking for is that slope of -1, and we get it right at that green line I've highlighted. So the leftmost slope there is, so these slopes are graphed on the right. Now, someone want to say, well, you should do some kind of more interpolation or something like that. Okay, I think we're still pretty far from, so these are simulations at 1,024 cubed. This is 3 billion unknowns. Each of these simulations is a little bit costly. So I think this graph is about 70 hours well, 70 times 1,000, so 70,000 hours of processor time, something like that. Anyway, so, we're just looking at the leftmost slope here. I mean, tomorrow, maybe somebody does a better simulation over here and you see this fall off. But we just wanted to look. And we plot the slope, and we plot the leftmost slope here over time. And right around that 4.2, I mean, it starts dipping a little bit earlier. So here's the -1 line. And you kind of see this, okay, I mean, this is maybe telling us that same Brachet blow up. Now, I mean, anybody in his audience could argue this is, you have some kind of double exponential growth. It's something like that. Okay. Again, no claims about blow up here. I'm just saying that actually, Bartek Protaj gave me a great phrase before he left when he was here a few weeks ago. He said it's not inconsistent with blow up. So that's the claim. Not inconsistent with blow up. Okay, does that make sense? All right. Well, I want to tell you more about, so that's the blow up picture. That's this backdoor to blow up that I wanted to mention. But I thought I'd kind of sketch out some other things that are happening with this Voigt regularization. And normally I put that stuff at the end, and that's a big punchline, but I'm reversing it this time just because, for fun. Okay, so let's take a look at, hey, who doesn't love Berger's equation, right? I mean, okay, so we'll start with Berger's equation there, but then we'll do Voigt regularization, right? Which actually has a different name. It's the Benjamin-Bonin-Mahoney equation for water waves. And we're just trying to get a feel for how it works. So they talked about this in 1972. You get the same kind of conservation law here. And if you, let's linearize the equation just to get a feel for it. So here, instead of ux, I'm just a constant times ux. So it happens. So we're moving to some velocity c. Again, take Fourier transform and rearrange things. And we get something like this. And what do you see? Well, I've got an I here, right, because of the transport. And then this piece is giving me each wave mode gives me each wave mode now has a different speed, right? This is dispersion, right? So now you have this thing is trying to spread out, which is exactly what you'd expect from some kind of water wave equation. Okay, these are reminders to switch your interlude. So let's take a look at what this thing looks like. And I'm going to remind you briefly of Berger's, viscous Berger's. Viscous Berger's. So I start off with the blob there. This is the spectrum on the right. And I just let it go. And if I have some viscosity, the thing goes, right? Viscous Berger's. Terrible name for a restaurant. Next. Decrease the viscosity a little. And you get a sharper, right? I mean, I think everybody is aware of this, but I'm just kind of putting you in the setting of the right. We get a more intense gradient stuff. Okay. Okay. This one under resolve. He's going to show you one. bit under-resolved. So this is, right, so our spectrum, I no longer consider this any kind of reasonable kind of computational picture here. The spectrum is under-resolved, and you see this kind of Gibbs phenomenon. And if you just turn it off, if you run the Inviscid case, you just get garbage pretty quickly. Okay, right, this is PDE's 101. Okay, now let's turn on some, right, so we'll turn on some alpha, but I'll keep the viscosity off. And remember this dispersion. So this is now, this is the nonlinear equation. But what happens, the singularity starts to form, but then, right, it disperses. Right, the singularity is going to form because you get some sort of alignment of wave modes in space, right? All the energy is sort of spatially concentrated, but they're running out at different speeds because each wave mode has a different speed because of that dispersion relationship we saw. And so you get this sort of attempt to align, and the more they try to align, the more they're shot off in different directions. And so you get this, it's periodic, so it never wraps around it. Okay, if alpha is smaller, so if you remember the kind of characteristic size of those, you get finer waves. Right? The alpha really is kind of controlling some kind of a length scale. Now, to me, this does not look very much like, say, burgers, right? It's looking definitely like some kind of nice dispersive equation, but you know, this is we're seeing something a little more wonky going on. So we'll come back to that. But, okay. Here. Yeah, so we did that. But, right, so now you can run the same test. You can say, okay, well, I know that burgers blows up, inviscid burgers, and I know that viscous burgers does not blow up, right? And so what happens if I run the same kind of blow-up test on those equations, which we just sort of did as a check. And, right, so you get a detection of blow-up at roughly the time you expect burgers to blow up. Here's that graph down below -1. And if you add viscosity, you don't have that. So it's in fact far away from that -1 thing. This is mostly just, I mean, I'm not trying to convince you of anything. This was just me trying to sleep better at night. Right? So that's something. Yeah, please.
Yeah, so you seem to get this minimum global minimum,
Yeah.
and it goes up again.
Yeah.
Same in the.
Yeah, it was the same. Yeah, if we go back to the.
Is there any reason for that, or was that just the code giving up?
It's a good question. I don't know. I mean, maybe some kind of like entropy catastrophe setting in, maybe, right? I mean, singularity set is. Yeah, I don't have a good answer. It's a really interesting question. Yeah, I don't know. I mean, if in some sense, if right, I mean that shock energy. I mean, at the level of where alpha is positive, that shock energy, and I just think about this in terms of the dispersive effect, is now kind of right. You try to form a shock, and then everything just kind of spreads out. But in the limit, well, I don't know. I mean, then we have to keep pushing here, and we, in some sense, need infinite resolution to keep pushing this plot to the left. So, yeah, it's a great question. Okay. Now, just I tell you that it works for other stuff. So you do some MHD. Mouse modes for no good reason. Here's MHD equations. I think most of you know about these, but if you don't, Navier-Stokes is part of this. If I set B equal to 0, so B is a magnetic field. If I set B equal to 0, then I get back Navier-Stokes, at least formally. Right, but I have this sort of, I mean, essentially I have an equation that looks exactly like a vortex, a vorticity stretching term, and then I have the Lorentz force, beta grad T driving everything. So I mean, this is obviously harder than Navier-Stokes in the sense that it contains Navier-Stokes in a special case. Hey, there's Navier-Stokes. So I don't have any viscosity here, but if you put on this Voigt term, now once you have a hammer, then everything becomes a nail. All right, so you can put alpha terms on both of those, and just alpha m means it can be a different alpha. You get global well closeness, at least for one thing that's kind of funny about this is we don't get much in L2, right? And we want our initial data, we started in H1 because, right, so your gradient is in L2 because again, you don't have this smoothing power. And that's also true for just the Euler case or the Voigt case. Same thing with Boussinesq. Oh, I used to have another slide. So you can do a couple other things. You can say not put it on the second term, but then at least in 3D, as far as we can tell, you do need some viscosity on the magnetic term. Okay, so similar stuff here. So this is right Boussinesq equations, and it the message is it works if we put this on. I mean, it's not too hard. Once you control the gradient and the momentum equation, you don't need all that. Much more control than that. So a lot of this is if you saw the dates there, they're a bit older references, but I thought I'd tell you something a little bit newer. So this is one that I've been having some fun playing around with lately. This equation by itself. So if we start with Navier-Stokes and take the curl, right? And you know you get the curl equation, right? The vorticity equation. But then I use this vector identity, which is maybe my favorite vector identity in the world, which is this little guy. Very useful for computations because I can now, I have a gradient. So you peeled off some of the gradient of the denominator term, and then you shove him over here, right? And if you're simulating, by the way, if you're doing some computations, you just forget what this is, and you project onto divergence-free spaces. You don't care what this piece is. And this is nice over here because you have fewer derivatives to compute. And if you're doing spectral computations, you like this, fewer products, right? Because you have 6 products here versus 9 up there. And anyway, you don't have to compute 9 gradients, you have to compute 6 gradients. So it's kind of a nicer way to do things computationally. And it's also nice because now you start to see, right, this is sort of a rotational piece. So Navier-Stokes wants to rotate things and then keep them divergence free. That's what it wants to do. But I don't know exactly where this first people who first looked at this, but goes back a while. I'll make some references in the next slide. But one idea is to consider these as 2 separate equations. So of course you can go back from the vorticity equation to the momentum equation by the VOC-VAR for that, at least once a day, right? That's daily vitamins, VOC-VAR for the last few weeks. So here, instead of omega for vorticity, just write W, because W is not the vorticity, it's just some guy that solves this equation. And now I have a 2-way coupling of the equations, and there's been some nice work on this. So by a lot of authors here, so going back at least to the 90s, but there's been some pretty cool work lately by Alshansky and Leo Repos. And, yeah.
If I think of this, or a liquid problem like this formulation, and consider the stress as a separate quantity. Here you say the verticity, right? If you consider the stress, you consider stress as a separate, then you have a constraint.
I don't know. I'd like to talk more about it. Yeah, that's interesting. I mean, so conceptually, you just decouple. You just don't use the VOC-VAR. Pi, by the way, is.
But the initial data is the same, right? So.
Yeah, initial data is the same. So formally, it's the same equation, right? We're not. Yeah. So if but it works as, I mean, so this kind of gains some traction in the computational community because it sort of gives you additional stabilization.
So we don't carry uniqueness, right? So you start.
Yeah.
We don't. No uniqueness.
Yeah, you don't know uniqueness. If you had uniqueness. Yeah, exactly.
But I mean, it's a bit
Or,
like
yeah.
conservative versus non-conservative numerical schemes. If you do this numerically, you will lose the rotor along the way.
Yeah. So yeah, exactly. So
I mean, W equal curl U will not be satisfied after some time because of numerical error.
Yeah, that's true. So you get sort of divergence, but it seems to kind of give a nice stable simulation. Seems to be nice.
Mr. Reference, I think you've got your effective linearity. Wrong side.
Yeah, omega W cross U. That's a right side. You flip that. It's
You
derivative.
only go with the T plus U double.
Yeah, if you go back to this guy, then it's, sometimes it's written, other, right, if you swap the cross product, then you get a minus, so sometimes you see it the other way around, but yeah, it's derivative on.
Vorticity has to be the other
No?
non-linear terms, transform terms have.
Oh, are you talking about this one?
Yes.
Oh, I'm sorry, yeah, that is backwards, yeah, sorry. Yeah, that's a typo, sorry. Yeah, that's oh, horrible, okay. Yeah, thanks. Yeah. Okay. All right, so of course, global oppositeness for this is open. But, and, so you have regularizations. If you have a regularization of Navier-Stokes, your favorite regularization, you just take the curl, forget the Biot-Savart law, and now you have another regularization. But you've got regularization in both. But we have, well, maybe you could just regularize one of them, right? So just put some kind of, so pick my favorite regularization out of my pocket, which is usually Voigt these days. So put Voigt regularization on the first guy and forget it on the second one. With the hope that, computationally, and we haven't tested this yet computationally, but that you should see some better, some sort of better, the typo has persisted, hasn't it? You should see some better, at least vorticity structures developing. And we saw this actually back, we did something like this for MHD back in 2012. And we saw that the Voigt kind of messed up the velocity a little bit, but had kind of a nice, preserved the structures of the current density rather nicely. So anyway, so we tried it. And yeah, you can even do this with some physical boundary conditions. Here we just looked at it in a periodic case, and you can prove global oppositeness for this model. It's a little bit funny. It's less straightforward than I thought it would be. You kind of have to, and you get convergence. You could blow up criterion. Comments about global oppositeness here. Yeah. So the you get something a little bit funny for this one. So it turned out you have to end up estimating the velocity first. So if you think, okay, well, this, by the way, so this is this might remind you really strongly of MHD, right? Because, just go back to this guy, right? This is MHD if I put omega dot grad omega back in the momentum equation. It's the same system. And if I don't, then, but that Lorentz force helps you in MHD because it gives you a nice cancellation when you put things back together. You don't have that sort of helping by the Lorentz force in terms of getting symmetry. But at least with this Voigt regularization of one of the equations, you can still get well oppositeness. But the idea is to notice that back in the sorry, I'm flipping back and forth. Back in this system, you can get bound by taking in a product with U. This term is still going to cancel, not because of any kind of nice symmetry, but just because the cross product is orthogonal to the things that you cross producted with, so that you just get a nice estimate on U to begin with. Then you go to an estimate on W. So you don't do it like MHD where you add. You have to kind of bootstrap it. But you can do it, and it's a mess of W's and omegas, but it works. Okay. Yeah. All right. I wanted to say something about Navier-Stokes. If I got a couple, do we go to a 5 or we stop a little bit? Wait, what's the normal stop? Or I guess it's not quite there anyway. Okay. Well, I had a little bit, but I'm almost done. I can stop anytime. Okay, yeah. So what about Navier-Stokes' Voigt, right? So I showed you that things kind of get a little bit funny there. In the case where you looked at Euler, or you get this sort of dispersive thing, which looks a little funny when you have no viscosity. But here, let me put some viscosity back. And so you get, right, so we didn't think about this for a long time, at least I didn't think about it for a long time, because I already had an L infinity time bound on the gradient, right? Why do I need viscosity to give me an L2 bound time on the gradient? But it's because, right, then I get something independent of alpha. So I get some kind of bound independent of alpha. So let's see. Yeah, okay. So let's take a look make some simulations. So if I put both an alpha and a nu, so what you see is that dispersive wave trying to peel off, but the viscosity sort of prevents that from happening. So here we get this thing tilting up, right? The singularity is dispersed, so it's not a singularity, but then the viscosity sort of prevents that dispersive wave from shooting off. So my feeling now is that I don't know exactly what this thing says about Euler, other than some of the book criteria stuff that was mentioned earlier. But at the very least, right, we get this. It seems to be kind of maybe nicer in the Navier-Stokes case or the viscous case. Okay. Yeah. Well, so if you take something, so this one is actually one of those under-resolved ones we looked at. So what if you take something very under-resolved? Right? So this is still under-resolved, but you don't get it somehow controls the shock maybe a little bit better. So you're still getting a lot of that kind of dispersive wave coming off of here. So that's not right. That's just some kind of dispersive front. But it's somehow more controlled. I don't know what you exactly think about this, but back to that. Right. So so now the thought is, okay, maybe this is kind of giving you some sort of nice simulation, right? Where I saw this thing about Berselli and Spirito showing super weak solutions in the alpha goes to zero limit. And this is kind of nice again because you don't have to modify boundary conditions. So maybe there's some, at least for the Navier-Stokes Voigt case, this is maybe kind of a nice thing to look at in the viscous case. But what happens as alpha goes to zero while you also send this viscosity to zero? So this is kind of like some ongoing work now with Theo Grivas and Vincent Martinez. Although things kind of got delayed a little bit by COVID, but now we're starting to wonder, if I send alpha to zero quickly and then nu to zero slowly, I get something which is, say, more Navier-Stokes-like. If I send alpha to zero slowly and then nu to zero quickly, I get something which is at least has a sort of dispersive character, and we know at least in the L2 norm we get convergence to Euler at least before blow-up time. So maybe, and this is just, it's fun to have wild ideas at 5 o'clock. So this is one of those. Maybe this is some way of selecting different solutions of Euler. Maybe this is just pure guess, right? But maybe there's something here where we can. By sending alpha and nu to zero at different rates depending on each other, maybe we can see sort of different character of Euler. Okay, so it says simulations if time. Maybe there's a couple.
But that's still in the periodic.
Is that?
That's
Yeah,
still
just
in the boundary.
they're involved in periodics. Yeah. I mean, I think it's maybe an interesting, right? Because this is a regularization. So you have well-posedness in bounded domain with the boundary conditions. So what happens with the limits of the boundary?
But this continuity is hard for
Yeah.
infinity. Regularity doesn't help.
Yeah. So I don't know. I mean, I don't have anything to say about it, but it'd be interesting. Okay. So I thought I'd just end with a couple simulations. These are slightly under-resolved because I actually did these I started them. Greg's, my office mate, has been hearing these run in the background. So I was trying to do something resolved, but they're close to resolved. And I just thought I'd show them for a little bit of fun for 2D Navier-Stokes. So you saw the 1D pictures. Here's some 2D pictures. So that's this one is nearly resolved. I'm sorry about the bouncy thing on the right hand side. So this is just 2D Navier-Stokes. With viscosity, no alpha there. And you're looking at the vorticity on the left-hand side. See, I'm cheating a little here with the slight under resolution.
You linear driving? Just
What's that? This is just Navier-Stokes, 2D Navier-Stokes periodic domain forced. It's forced. Yeah, forced. Yeah. So yeah, they didn't put force on this. This was forced. Great. if I put some alpha on that, I'm going to do my best not to make any comments about this. So definitely, sorry, this is alpha equals 0. This is a this is a quarter size of the domain. So this is unresolved, right? So the previous domain was 1024 by 1024. This is 256 by 256. So it's very unresolved. We're still getting something, but maybe this is just garbage. Right? The forcing in this case is from a paper in 2008 by Olson and Titi. It's annular forcing in a ring. Right? So Voigt-type 10 and 11, or 10 and 12. 10 and 11.7. Yeah. But if it, sorry, no, that's not. That's this one to show you. Come on. Here we go. Put a little bit of alpha there. You see some kind of. And by the way, I think also in 2D, this might not be kind of giving you the right picture. So maybe, I debated a lot about showing these or not showing them. But in 2D, you have inverse cascade, right? Which is maybe kind of contaminated here a little bit by this alpha. So you can think about spectral Voigt kind of thing where you just do this on the high modes. So this is with alpha. See, the spectrum is a little bit more under control than the low resolution case. So this is still lower resolution than you want. But if you stare at these a little bit, you see kind of similar structures evolve at similar times. Of course, what we're really trying to do here is kind of capture some kind of statistical flavor. And I think questions there are still fairly open.
What are you trying to achieve with these?
Is that?
What are these trying to achieve?
Just showing you, it's mostly just showing pretty colors at 5 o'clock. But yeah, just showing you that if you get some, but by going to lower resolution, but turning on alpha, right, you seem to be able to at least maybe control the solution a little bit better, whether or not you're actually getting, sort of something that is like a kind of a subgrid scale model, I think is still wide open. But I just kind of wanted to put these up here and,
So
judge for yourself.
ideally, on low resolution plus alpha to look like high resolution.
Yeah. And so, I don't know, then, they a little bit similar. Okay, well, that's, since it is 5 o'clock, I'm going to say thank you.
Yes. Well, yeah.
I'm assuming your Taylor Green calculations are something like 1,000 cube mesh, and you're running code periodic redirections. It's not taking advantage of any of this.
Correct, yeah. I mean, it's using that omega cross U nonlinearity, but not the velocity-vorticity formulation, but just the standard omega cross U.
Fine. Well, you're talking about running with the plan vector. Yeah, that's fine. Something like that. We've always done. Okay, Steve, or
sorry.
discovered
Okay.
did this.
No, I am using 2/3 de-aliasing.
You only do 2D de-aliasing?
2/3 de-aliasing.
No, okay,
Yeah.
That's what all of us.
Yeah, I try to make it very standard and controversial. I mean, it's
Now, there's
really
a
controversial.
reason why the latest probably the last paper by James Gell from 2012.
Yeah.
They're doing 4,096 points, but they have all the symmetries in there. So effectively, they're doing 16,000.
Yeah.
Okay. So I would be very skeptical about whether you can come anywhere near even tiny 3.8. So they went to 4.
Okay.
Okay.
Yeah.
So with that comment, we need to get you a code that has all the symmetries.
Oh, I would love that. I thought about this, but yeah, that would be great.
I can give you two sources. We can discuss.
Okay, yeah.
It's doable.
Okay, let's talk offline.
We have to go
That'd be great.
beyond Mach ATMs back to some degree, but discuss.
Okay,
And last thing is, I know, so a real hard thing to do is to compare anyone else's Taylor Green to results from Brachet, because everything is, all the results are this analyticity business, which seems to be in hyperspace.
Yeah.
Okay. Easy thing to do is if someone generated Euler or Euler-Voigt vorticity moments of the sort that John Gibbon has been promoting analytically, which I used in my 2013 paper, very convincingly showed that the anti-parallel was definitely not singular.
yeah,
Okay. So the thing to do is get those moments and know what the L infinities do from that. That thing is, I know what the L infinity is doing for the last Brachet calculation. So, and I know what the doubly exponential coefficients are. Okay, Miguel will put up the table.
Okay.
Okay, so we can.
well, maybe we should talk offline.
We'll talk-
I'd love to talk to you more about that. Yeah.
I know I have this. This is the direction.
Great, yeah, thanks. Yeah,
SQG.
SQG. So I didn't know that it wasn't done for SQG until Diego said it. I mean, so it was done. Right, so there's only like 5 papers in computational tests. You're talking about computational, right? Yeah. Yeah. I mean, I don't want to do it right now. Yeah.
So it is as a format.
Okay.
Because apparently we're having some technical.
Yeah.
issues.
Here, I can pull it up. So you can see.
No, I don't know that he puts it in the chat. So he says, concerning the last simulation, observe that this Voigt regularization, all it does, it inhibits the cascade of energy in 3D Navier-Stokes and S3 in the 2D case. It does not affect the dynamics of scale smaller than alpha, and this is why we have inverse cascading.
Yeah, so I don't really feel like
And then this was done computationally, I guess, in the shell model.
yeah. Oh, yeah, that's right. Yeah, so yeah.
Make that comment?
Idris. Yeah, so I don't think that 2D is necessarily a great setting for this. I mostly just kind of wanted to show that you're getting some, in lower resolution, you do get some kind of thing that looks a bit like a higher resolution. But again, because of the inverse cascade, Idris is exactly right. And I tried to kind of comment on this earlier. It's not quite. Yeah, it'd be better to show you some 3D simulations, but I didn't have time. So it would take a long time. Yeah. Question?
Can we go back to the MHD question?
Yeah.
Page 31.
Page 30, okay, maybe somewhere here.
Oh, yes, that's the one. Yeah. In induction equation is linear in magnetic field.
Yeah,
So I wonder, maybe you don't need that regularization term for now.
yeah,
You need
yeah.
that for the
So Daniel Catania did this.
But maybe not for the induction equation.
Yeah, that's what I thought. But it turns out we seem to need it. There's just.
Just half of the less than one.
Oh, yeah, okay, yeah, half, yeah, so fractional powers, so I didn't mention fractional powers, I'm really interested in, basically because fractional powers give you some amount of dissipation. So fractional powers, I think, is a cool thing to look at for this. But yeah, you may not need quite the full dissipation there. You need just a little bit extra for emission. So if you put viscosity on, that's enough. So you can put viscosity in the magnetic equation and no alpha regularization, and then you get both those units. But you need something. You need a little bit.
There is the Lorentz force on the right hand side of the momentum equation, but the induction equation is linear in magnetic field.
Yeah.
So it may be very nice. as long as we get velocity control.
Yeah, I mean, what I
do velocity, then the induction equation will be okay.
Yeah, I mean, what I don't know how to do is put alpha equals 0 and put no diffusion on the magnetic equation. That I don't, in 3D, that I don't know how to do. Daniel Cataneda did it in 2D, but he had to have hyper dissipation on the momentum equation. This was like in 2009. I mean, he was looking at simplified Bernina, so it's a little bit different than hyper diffusion. Yeah, so fractional though, yeah, fractional, I think there's a lot of hope there.
It's a good problem.
Yeah.
I'm not sure.
Yeah, I agree with
That's
that. I
pretty
agree.
critical. Half of what life, that's critical. Then you're going to control H1
Yeah.
right? So that's,
So you should be fine.
and then you use the Spirelli solution.
Yeah.
So there is another comment from Andres. Also, KDV does not converge to borders when the expression coefficient tends to 0 after the shock, but it is okay before the shock. The same is here. One cannot capture the entropy solution by the BBM regularization, and this is not the purpose.
Right. Yeah, you're not trying to capture any resolution. Yeah, just that's exactly right.
There are comments, questions? Well, a reminder, we have one talk tomorrow morning by Bob, and then we have a talk on Thursday.
And the schedule's been corrected.
Well, not yet, but I'll try tomorrow morning.
It'll be starting at 11.
Start at
We're
this room?
gonna try to move it at 11.
Is it this room?
10:30. Yes,
Someone-
it will be this.
After my discussion, what it is.
Yeah,
Okay.
it's supposed to be at 11 tomorrow. Yeah, I'll send the message. After I talk to the staff tomorrow, I'll send the message.
Thank you.
Okay.
And the other talk is at one.
It's at 4 on Thursday. But there is a talk by the other program at 4 tomorrow, but I'm not in charge. No, the other one.
Anyhow,